First off, in this video we're going to look at some properties of the matrix inverse. So if A and B are non-singular, and this just means that a determinant is non-zero and therefore they have inverses, and then A inverse is equal to A. This makes sense. If we invert the inverse of a matrix, we get that matrix back. And this comes from, if you note that the definition of the matrix inverse is that A inverse multiplied by A is equal to the identity matrix is equal to A multiplied by A inverse. So it makes sense that if you invert the inverse matrix, you get back to the matrix itself. Okay. Oh yeah, and I just wanted to put this because this is like our formal definition of A inverse rather than the calculations we've done in other videos. If we multiply two matrices A and B, then we find the inverse of that. That's equal to the inverse of the matrix B multiplied by the inverse of the matrix A. And it's important to note in matrix multiplication the order matters, because A, B does not equal BA necessarily. So it might do in some special cases, but in general that's not true. So the important thing here is we swap over A and B. And the last one, if we take the transpose of a matrix A and invert that, that's equal to the inverse of A transposed. Okay, so those are three properties. Next we're going to look at solving simultaneous equations with matrices. Right, we're going to solve this set of simultaneous equations using what we learned about matrices and their inverses. Just a quick note, this method can be applied directly to the 3x3 case where we got simultaneous equations, three equations with three unknowns, so x, y, z. You just do exactly the same method. So you write a coefficient matrix, so you get 2, 3, not x, 1 minus 2. You multiply this by x, y, and you set this equal to the vector 11 minus 5. Okay, this makes sense because when you multiply out this matrix, you get 2x plus 3y on this top row, which is then equal to 11, and you get 1x minus 2y is equal to minus 5 on this bottom row. That's a simultaneous equation, so this matrix equation is therefore true. Note in the 3x3 case, you'd have your three equations, so you'd still have your coefficient matrix, but then you'd have x, y, z, and then this would be equal to three numbers here. Okay, so if you do want to try some examples like that. Right, now we're going to call this coefficient matrix A, and we're going to find the inverse of A. A inverse is equal to 1 over minus 7, calculating the determinant. 2 times minus 2 is minus 4, and then we want to do minus 3, and then we swap these over, so we get minus 2, 2, and then we change the signs of these two elements, so we get minus 1 and 3 there, and minus 3, and now we're going to multiply both sides of this equation from the left, and you have to multiply it from the same side. That's important. Obviously if you multiply A by A inverse, they just cancel each other out, so we get xy is equal to minus 1/7 minus 2 minus 3 minus 1 2 multiplied by 11 minus 5. If you do this matrix multiplication, so we get minus 2 times minus 11 minus minus 3 times minus 5, it comes out as minus 7, and then we do so that's minus 7, and then we get minus 1 times by 11, that's minus 11, minus 2, plus 2 times minus 5, so that's minus 10, so that comes out as minus 21, and then this is equal to 1, 3, and this gives us that x is equal to 1 and y is equal to 3. So you would get the same result if you show that if you solve this a conventional way, but sometimes this matrix inverse way is a nice way of doing it. It's possibly no quicker in the 2x2 case. 3x3 matrices, it's a pretty good method for solving them rather than elimination in 3x3, so I would choose it there. And you know, if you have to do a 4x4 system, then I doubt you would on any of your exam questions. That'd be a bit harsh and a bit time consuming, so, but anyway, you can try it as an exercise if you want. So hopefully you can see how this works. Because we're multiplying by the inverse, we get this vector of xy, and then if xy as a vector is equal to some other vector here, well, the x component of this vector, the 1 must be equal to x here, or the ith component I should say, should be equal to the ith component here, which is x, and the jth component y should be equal to the jth component here, otherwise those vectors are not equal. So x equals 1 and y is equal to 3. You can check this. 2 times 1 plus 3 times 3 is equal to 2 plus 9 is equal to 11. And then 1 minus 2 times 3 equal to 1 minus 6 is equal to minus 5. Okay, so it does work. I encourage you to try an example, the 3x3 case, and this will help you practice finding the inverse of a 3x3 matrix as well. And if you don't, if you're not sure of your result, you can always use if you've got a graphical calculator to solve the simultaneous equations for you to check that you get the right values. If you have any questions about this, please be sure to let me know down in the comments. If you did enjoy this video, please support me by liking and subscribing to the channel, and I hope to see you in the next one.